Dear students, welcome to this LMS program developed by Chamarajanagar University, Mysore Universities and various universities across Karnataka. I am Dr. Chinmay Bhatt, Assistant Professor, Government Christian College, Chamarajanagar. I teach chemistry to BSc students. I teach organic, inorganic, physical. In this LMS, I have focused few lectures on physical chemistry. So I request you to make use of this. So this is the syllabus of chemistry for BSc degree program. This is same for University of Mysore and Chamarajanagar. Started from 24-25. So this syllabus in the theory sessions divided into three parts: organic, inorganic chemistry, organic chemistry, and physical chemistry. So each one is of 15 hours. Inorganic 15, organic 15, physical 15. The first unit is inorganic chemistry, second unit is organic chemistry, and third unit, unit 3, is physical chemistry of 15 hours. So I am covering these two modules, that is gaseous state and molecular weight velocities, and also behavior of real gases. Going ahead, I will also cover critical phenomenon. Okay, so totally 1, 2, 3, 4 modules of each of 8 hours total. So I'll be covering. Okay, we'll go through one by one. First we will start with gaseous state. Now you all know what is gaseous state. You know there are three states of matter, namely solid, liquid and gas. So this is gaseous state where molecules are far away. Here molecules are a bit closer, that's why liquid. Molecules are a bit closer, very much closer, and tightly packed, so they are solid. We'll understand this through these animated videos. This PET Colorado is a software wherein you can see various animation simulations. It's an interactive simulation software. You can visualize various things related to gas, liquid, and various organic reactions, physical chemistry reactions, also physics, chemistry. Okay, we'll go to the states. So this is solid state. You can see in this container a solid is kept where molecules are tightly packed. They are held together by some force of attraction. It may be ionic attraction, covalent, or it may be van der Waals, whatever. But there is a cohesive force which is cohesive as well as adhesive force. So it is working strongly, so they are held together. But if you go to liquid phase, you can see they are separated by some gap. So they are diffused in the diffused state compared to the solid. Okay. So you can see in the liquid phase, the molecules are having some space in between. Okay. They are not tightly held as compared to solid state. Move on to gaseous state. You can see they are further diffused. They are far away from one another compared to that in liquid and solid state. You can see molecules are moving freely, randomly, they are colliding and they are colliding against the walls of the container, colliding against each other, moving in all the direction, and it's a random motion completely, and there's a lots of space in between these molecules. It may be any gas. Now this is neon. Suppose you go to argon. This is again argon gas, monatomic gas. Go to oxygen, you can see oxygen gas O2, it's a diatomic gas. If you go to water, which is triatomic gas, vapor phase. So in all these cases, gaseous state, you see the molecules are loosely held. But when you go to liquid state, you can see water, when it turns to liquid water, they are closely held. When you go to solid state again, you know this tetragonal structure. They are through hydrogen bonding, how they are held together. The solid state, that is nothing but ice. Okay. So now I'll show you the effect of temperature on any gas. We will take argon. I go to gaseous state, neon. I'll go to gaseous state. I'll increase the temperature. You see it here. Temperature will increase here. This is a thermometer. See what happens, you can see here. See, I'm heating. See, temperature is increasing. 71, 72, 73. So what is happening? What is happening to molecules? Molecules are moving faster, right? See, when I increase the temperature further, molecules started moving faster, right? If you go on increasing, you can see it. They started moving faster and faster, right? And collision is increased. Number of collisions between the molecules as well as with the container walls. They are increasing, right? Okay. Now I will decrease the temperature. Okay. I will cool it. So now what happens? The speed or the energy of these gaseous molecules, they are coming down. See, they are slowly, they are decreasing, right? The speed is decreasing. You can make it minus 43 or okay. You can take any one of these. See, if I heat it, the molecules will start moving faster. If I cool it, molecules are moving slowly and coming close to one another. So this is why I have shown you, because this velocity or the speed of the molecules, whichever may be there in the state, especially in the gaseous state, you can see that depends on temperature. Okay, also the energy of the molecules depends on temperature. They increase with increase in temperature. Okay, both speed and energy. So let's go back to the states of matter: solid, liquid, and gas. Gas molecules are loosely held, far apart from each other, and there is a space between these gaseous molecules. What is present in the space? You may ask this question, because what can be present here? If there are no molecules, what can be present here? So scientists say that it's just an empty space or vacuum. Bit difficult to realize, but it is an empty space. So these are the key characteristics of gaseous state. You know, gases does not have any particular volume. It takes the volume of the container. They are highly compressible. That's how we can convert gas into liquid. For example, in your home, LPG gas. You bring LPG cylinder. LPG, that is liquefied petroleum gas, is basically N-butane. N-butane gas is compressed under high pressure at around minus 1 degree Celsius. It will convert to liquid. N-butane liquid. So whatever LPG cylinder you get, that contains N-butane liquid. When you release outside at normal temperature, that is room temperature, that gets converted to gas. So This indicates gases are compressible. Okay, they can be expanded, expansibility. When you heat it, they readily expand. Low density compared to solid and gases, solid and liquids, gases have lower density. Diffusion, they can diffuse, they can mix each other. That's why you see outside it is not like oxygen separate, nitrogen separate, hydrogen separate. They're all mixed. Whatever we breathe inside, it's total air. We don't breathe separately oxygen. We don't have any filter in the nose. So it's all air what we take. Okay, mostly some of the books in the primary school you must have seen, they say we inhale oxygen. It cannot happen. We inhale air, but our body uses mostly oxygen and again gives out air with more content of carbon dioxide. Okay, that's what the process is. Okay, all what you see outside, they are gases, they are mixed, and pressure exertion, they exert pressure in all the direction. Okay, these are the key characteristics of gaseous state. You know the examples of common gases: air, which is a mixture of gases, and oxygen, nitrogen, carbon dioxide, helium. It can be neon, argon, all these. There are many gases. Again, methane, ethane. These gases are naturally present around. Some more, any gas, we can't see any gas, but we can only feel it. So it may be oxygen or nitrogen. Unless you liquefy, you cannot see any gas. Whatever you see outside, that sometimes when you feel the air, whatever you see is dust particle, not the air. So air we can't see, but when you condense it under high pressure and low temperature, we can see the gases converting into liquid. In the liquid form, we can see it. Okay. Then coming to kinetic theory of gases, these things you have already studied in your 11th standard. These are the postulates of kinetic theory of gases. Please note one thing, this kinetic theory of gases is valid only for ideal gas. Okay, I'll come to that, what is ideal gas and what is real gas. So these are the postulates. Gases are composed of large number of tiny particles, which you know, and they are separated by vast distance. You have already seen it. These particles are in constant random motion. This also you have seen, because they move, because in any direction they can move because they are not tightly held. And collision between the gas particles and with the container are perfectly elastic. As I told you students, this is valid only for ideal gas, not for non-ideal or real gases. It cannot be perfectly elastic in all the cases. Okay, but for ideal gases it is assumed that collisions are elastic. There are no significant attractive or repulsive forces in the ideal gas, okay, but cannot happen in the real gas. So average kinetic energy of the gas particle is proportional to temperature. This I have shown you in the animation, that kinetic energy as well as the speed increases with increase in temperature. Okay. Coming to this kinetic gas equation, which is valid mainly for ideal gas or the gases which behave ideally, approximately, okay, that is PV is equal to 1 by 3 mnc square, where c is mean of the squares of the molecular speed. Okay, that is mean square velocity it is. So m is the mass of the gas molecule, of a single gas molecule, and n is the total number of molecules in the gas sample, I mean which you consider for experimentation. You can call it 1 by 3 mnc square or 1 by 3 rho c square. Okay, this rho is nothing but density of the gas. So coming to this ideal gas, I think you have studied this in 11th standard, concept of ideal gas. But let me tell you one thing, there is no ideal gas in the world. Okay, there is no ideal gas. It is just a concept. It is just a hypothetical gas, or it is just an assumption made. It is like ideal person, we call it as. But it's no one who is ideal. But person can approach ideal behavior by making habits of good manners. Similarly, there cannot be an ideal gas, it's just a hypothesis, but gases can approach ideal behavior. This is what has to be, this is what we should know before going ahead. Okay. Ideal gases strictly obey the ideal gas law. This is PV is equal to nRT is the ideal gas law. Pressure, volume, N is number of moles, R is gas constant, and T is temperature. This is derived from Boyle's law and Charles law, which you know it. As it is not included in the syllabus, I am not going to discuss the laws of gases. Hope you all know it. They strictly obey the ideal gas law, PV is equal to nRT under all conditions. So these kinetic theory which I have discussed, they are valid for ideal gases strictly. Negligible particle volume compared to total volume, no intermolecular force of attraction. Okay, that means ideal gas you can't convert it into liquid, because even if you compress it, compress means you increase the pressure, volume will decrease, certainly, no doubt. But how long? Volume will go on decreasing as you increase the pressure. It cannot be converted to liquid. So because there is no intermolecular forces between the particles. Elastic collisions means there is no energy loss. Collisions will be elastic. They continuously move in all the direction. Kinetic energy is proportional to temperature. These are the assumptions made towards ideal gas. Nothing but kinetic theory of gases. Postulates of kinetic theory of gases. These are the characteristics as I already told. They are hypothetical, does not exist in reality. They are infinitively compressible. You can compress as long as you want. They don't get converted to liquid. They don't, because it is infinitively compressible, they don't condense into liquid or solid. This is the ideal gas law. Now coming to real gas. What is a real gas? Whatever gases you see around, it may be carbon dioxide, nitrogen, oxygen, helium, I mean whatever you feel outside, they are all real gases. There is no ideal gas. So gases exist in reality. They are all real gases. Okay, and they don't follow the assumptions made for ideal gas laws. Okay, so the main characteristics are they possess definite volume and intermolecular force of attraction. It may be attraction or repulsion, but they have intermolecular forces. Okay, they have definite volume. We can't neglect the volume, because under high pressure and low temperature, volume should be considerable, especially bigger molecules like carbon dioxide gas, neon gases, or oxygen gas. Okay, they deviate from ideal behavior, particularly at higher pressure and low temperature. Okay, can condense into liquids or solid. Okay, can compress it at one stage. You can convert most of the gases into liquids, and they deviate from ideal behavior because their molecules occupy certain volumes. So this is noticeable at high pressure and low temperature. Okay, because the deviation is stronger at high pressure and low temperature. Some gases, not all, some gases approach ideal behavior at high temperature and low pressure. Okay, when the temperature is very high, pressure is very low, then some gases can approach ideal behavior. So this is different. But if you come other way around, at high pressure and low temperature, most of these gases show the deviation from ideal behavior. Okay, because the molecules come closer together. Okay, and interactions become prominent. And for real gases, you should always remember ideal gas law is not valid. That equation PV is equal to nRT is not valid. That's why another law or the equation is given by van der Waals. This is called van der Waals equation, considering force of attraction and the volume. That's why you know there is something called van der Waals force of attraction. Okay, he considers that, and he gives two correction terms A and B and added in that. So it becomes, instead of PV equal to nRT, it becomes P plus A n square upon V square into V minus NB equal to nRT for n moles of gases. For 1 mole, it takes the form P plus A upon V square into V minus V equal to RT. Okay, and T is temperature, R is the universal gas constant, V is volume, P is pressure. A and B are the gas constants given by van der Waals. A is for intermolecular attraction between the molecules or atoms. B is the van der Waals constant which accounts for finite volume of gas molecules. Okay, this is the list of differences between ideal and real gases. Ideal gases obey all gas laws under all conditions. Real gases obey gas laws only at low pressure and high temperature. Again, they don't completely obey, but they approach, okay, closely. There can be deviation at low pressure and high temperature. The volume occupied by ideal gases is negligible as compared to the total volume occupied by the gas, but the volume occupied by the molecules in the case of real gas is not negligible. The forces of attraction among the molecules are negligible. We should say there is no force of attraction or repulsion between the molecules. Here the forces of attraction are not negligible, especially under low temperature and high pressure. Okay, they obey ideal gas equation P equal to nRT. These real gases obey van der Waals equation. Okay, these are the differences between ideal gases and real gases. Please note that ideal gas doesn't exist, it's just hypothetical, and whatever we see or whatever we have around us, they are all real gases. These are some of the references books, very useful books, like which you can easily understand. Principle of Physical Chemistry by Puri Sharma and Patania. Very well written and very easy to understand. Again, this is a very nice book. Physical Chemistry by P.W. Atkins, a very good book. You can also read Elements of Physical Chemistry by P.W. Atkins. Bit basic level, this is at bit advanced level. And a very useful book I suggest everyone, Chemistry for Degree Students. There are series of books written by R.L. Madan. Please go through it, it's as per the UGC standard. And there are various online resources, you can go through them. Apart from Chemistry Live Text and Chemistry Steps, you have NPTEL, Khan Academy, and several other YouTubes developed by various universities across the globe. Okay, I request you to go through them. And also there are these videos developed by various professors available in MOOC and also EPG Pathshala. Okay, please go through them. Okay, hope you have understood. If you have any questions, please raise it. Okay, thank you very much.